Although I'm here on campus fairly often in joint research work, it's a real pleasure to be back here in this capacity. I'm honored and humbled to be presented this recognition. I think my first time on this campus would have been in the summer of 1978, perhaps, working with John Wainwright on some relativity programs using the CAML system for computer algebra, staying in Conrad Grebel College. And then I decided to come back here for graduate school because this was the only university that had both a relativity course and a computer algebra course. It was really, it was a unique spot in the world. And it's a real pleasure here to have some colleagues with whom I'm working today, and also some people from whom I took courses years ago. So it's very nice to be back. Now, we've inherited a president from your university. So one of the first things he did was we're no longer the University of Western Ontario. We're now Western University, and as Mark said, there are several other affiliations here. Some of the work that I'll talk about has taken place at these different places. The talk is about leading flying objects, and by leading we mean guiding, directing, or influencing the thing which is of greatest importance or degree. I think we know what we mean by flying, and we know what we mean by objects, but I'm not talking about any of these things in particular. It's the combination of things that matters, and so I'm really going to talk about duck shooting. All right, so flying objects, that's a euphemism for ducks, and the point is that when you want to shoot a duck, you have to start behind the duck and move your rifle until you're pointing beyond the duck, and then you pull the trigger if you want to hit it. All right. So I found an interesting article in the October 12, 1955 Lewiston Evening Journal. It's called "Aiming Ahead of Your Target is Important in Wing Shooting." And this is very relevant for software development or research in general. Now, this scan is not particularly good, so I've highlighted a couple of parts of it. All right, so the first thing is you can't hit him if you shoot behind him. All right, this I think is an important thing to think about when you're doing research. A lot of people, they finish their PhD and they continue to work on that problem for the next 30 years. And it's a problem that it's still interesting. There's still things to do, but it's not the next problem. So we need to think about what's the next thing we want to work on. And he gives some very important instructions, which I think are relevant to all of us. Okay, the first thing is you start your swing behind it. So if you want to build the next social software company or so on, you have to sort of start to catch up. You have to learn what's going on. You don't hold your gun still waiting for it to come to you. I think you have to go out and you have to find out what's going on there. Then you have to swing with it, following its flight and eventually overtaking it. And then once you pass it, you pull the trigger. All right, so that I think has as much relevance to software development and to research as it does to building companies, as it does to shooting ducks. So I'm going to tell a few stories about this, about these ideas, and I think Mark mentioned many of these things. I've got more stories here than would fit into the time available, so I'm going to breeze through some and go into a few more details about others. I understood from the invitation that there would be many people here who do not really know what computer algebra is, and there are many people here who are the leading experts in the field and everything in between. So it's going to be tough to say something that's meaningful at all moments, but hopefully there's something for everyone. So I'm going to start out with Maple. Maple is I think most people here are familiar with Maple. It's a software system for doing mathematics symbolically. So you can say that you want to differentiate some expression like that sign of something or other, and you get back your answer. You have no idea, well, maybe you do have an idea, how difficult it is to be sitting next to some interesting person on the airplane and they say, "So what do you do?" "Oh, I do software." "What kind of software?" And then you have to explain that. Okay, so I usually say, well, instead of using Excel to compute the numbers, imagine you could use the computer to figure out what the formula is to go in the cell. And I say, oh yeah, really? Oh yeah. So tell me, do you like swimming? Yeah, so it's just all right. So this project was initiated in December of 1980, and I joined in January of '81. Mark was saying about overlaps. I was still finishing my master's degree at the time in applied math, but I had an NSERC support, so I could do what I wanted because I didn't have to get support from anywhere else. And so joined the project. And it was and MapleSoft as a company was founded in 1988, and we have the honor of having both one of the founders and the president of the company here in the room today. So that's great. All right. So here's what Maple does. I think that for those who are not familiar with it, the thing to take away out of here is that you've got some, I wonder if the cursor works on this. It does, okay. So you've got input as some formulas and output as some formulas, and you can do things to transform the formulas. All right, so the idea is it was a lightweight design based on a compiled kernel and interpreted library. This was very different than the prevailing wisdom at the time. The idea was we wanted to be able to run dozens of students on a time-sharing system. I couldn't find a photograph of the Honeywell system we had at the very beginning, but we moved very quickly to a VAX. This is a VAX 11780. All right. Now, this is an example of shooting ahead of the target, because being able to run a dozen students on a time-sharing system translates pretty quickly to being able to run a single user on a personal computer. We never actually ran on this PC because its address space was too crippled, but we ran on the next generation pretty easily. And the nice thing about this is now we can do more in smaller places. So to be able to solve real research problems on a machine of this size is something that is a consequence of being able to run with dozens of students on a machine of that size. And these days, of course, you've got computer algebra running in things the size of a telephone. This is a TI Inspire device. And so one of the consequences of Maple having been developed here is the creation of the Ontario Research Centre for Computer Algebra. And in fact, one of our postdocs now at Texas Instruments and is the lead person in the computer algebra for that device. And so now Maple, one of its main thrusts is in computer-aided engineering. And here's the screenshot from Wikipedia of MapleSim working on an automotive problem. All right, so that worked out by aiming at a slightly different problem, so dozens of students on a time-sharing system, as opposed to a system that comes in and takes over the whole computer for one user, which was the prevailing way of doing things. Well, now we're able to solve things in a very different way than we otherwise would have. Okay, so moving on to Axiom and Aldor. The initial inspiration of this was a paper called A Language for Computational Algebra by Jenks and Traeger in 1981. This was the Snowbird ACM SIGSAM conference. And I remember that we went with Keith to the SIGSAM conference, and that was when Ronald Reagan fired all the air traffic controllers. And we had to drive back from that conference. I think that you'd driven there with Debbie, and I flew, and I couldn't fly back, and so I drove with you up to Alberta, and then flew back from there. So in any case, this paper, Language for Computational Algebra, was an inspired paper. It was talking about using a strongly typed language for generic algorithms, where the type system is based on modern algebra. And this was similar in some directions to my own thoughts I'd been having at the time. And we met the principles behind this paper at the Computers and Math Conference at the Quora Institute a couple of years later. I remember we drove down there with Keith in the car and a couple of other students with the Spectrix computer, which is about 1/3 the size of this and about 1/10 the power of my telephone. And we had some demonstrations of the software down there, and we met the principles behind this paper there. Now, we later learned that the things that were described in this paper were all cardboard cutouts. Okay, nothing actually worked. Okay, and so then I went and joined the team at IBM Research in 1984 to actually try to make this stuff work. And that was actually a lot of fun. And so this group at IBM Research was building this very ambitious system. At the time it was called Scratchpad 2. And so the programming language was using what are known as type categories and runtime generics. So many of the things that we're seeing now in programming languages such as Java with templates and with generics and C++ with templates and so on are similar in flavor to these things that we were seeing in the very early 80s there. So many things show up in mathematical computing before they show up in the general programming language world. I think partly because you've got complex, rich problem structure there, but also everything is well defined. So you're able to try out ideas and you know what's right and what's wrong, as opposed to some rule-based air traffic control system, which is very complicated, but there's no clear answer. In any case, this system was very difficult to see whether, to actually for it to get anywhere, because it was a large system shoehorned into a 24-bit address space, because of course it was an IBM 370, and those who might have used IBM 370 architecture will remember that although there were 32-bit words, the top byte didn't participate in the addressing, and so you've got this shared address space with the whole operating system, and you have to fit all your computer algebra system and so on into the 24 bits of addressability, and so it was very crowded. That's what this picture is. This is a goldfish bowl filled with goldfish. That's exactly what the address space of the Scratchpad system looked like. There was no room to put any more goldfish in it. And in fact, the group, we had a dedicated IBM mainframe that people could dial into and use for research purposes. It was based on the same model as the MC machine at MIT, where people could come in and try and solve the research problems on it. But even one instance of Scratchpad running on this machine, this IBM mainframe, would bring it to its knees. Right, so this is a situation where we were trying ambitious things, I think some far-looking ideas, but maybe a little bit too far ahead, because the hardware we weren't able to sort of have a very quick turnaround time in our experimentation, because the hardware just wasn't there to support at the time, even though everything we were trying to do is by now almost trivial. All right, so we moved to the Unix platform in 1987, and my main contribution there was to reinvent the language so that it had some kind of solid foundation based on dependent type theory, and built a C implementation of a standalone compiler that you could compile your computer algebra programs to either run on their own or inside the Axiom system or a number of different environments. We released this through the NAG Limited of numerical libraries fame as Axiom and Aldor in the early 90s. This failed commercially. It did not take off, partly through the exclusive lock-in to particular IBM hardware. Also, it was a very resource-intensive system, and it's had limited open source success since then. So here's something where I say it was maybe too early. The work was, I would say it was influential in the thinking of computer algebra and the way to work on these math problems. And it's shown up in systems from Tektronix. The template system of C++ has evolved directly because of Aldor. One of my PhD students was sharing an apartment with one of the folks working on the C++ template system, and there was a lot of cross-fertilization there. And then other computer algebra systems and math languages have followed it. So I'll move on now to something with a little bit of scientific technical content, and I'll go through it quickly and get on to the other stuff. All right, so I'll start off by asking, what is a polynomial GCD? I imagine there may be someone in the room here who does not know what a polynomial GCD is. So if I've got two polynomials P and Q, if I factor them, I can write them like that, and I can see that they've got a common factor. And a polynomial GCD is finding out what are the maximum common factors that they have together. And we'd like to be able to find that without actually factoring them. And so I'll call this the greatest common divisor of P and Q, and we can compute that using the Euclidean algorithm. Okay, now this is pretty clear. Now what happens when I have slightly different coefficients? Suppose I take that initial problem and I just perturb it a little tiny bit. Somehow we'd like to know that this is close to a problem where there are common factors, where there's a greatest common divisor. This has applications. For example, suppose I'm looking at the kinematics of a robot arm and expressed in terms of polynomials, and there's some natural reason why this ought to have a particular factored structure, but because there's a little bit of movement in the joint, I actually get this polynomial rather than the +1 at the end. I'd like to be able to find out what is the factorization of these things rather than saying, well, there's no common factors. Right. So here's an example of a problem that I started looking at together with, so this one has a GCD of 1, even though we'd like to find that it's close to something else. So now, there. So in 1995, the state of the art was, what we'll do is we'll run the Euclidean algorithm with a fuzzy zero test. Instead of asking, so the Euclidean algorithm has some steps and you stop when something's equal to 0. And so the way that things were done up till 1995 was to say, well, because we want to know whether we're just close to something, instead of asking whether we get down to 0, we'll just say it's okay if the answer is really small. And anybody with a mathematical background here would say, what on earth does this mean? You know, what's the what does the answer mean if you just run an algorithm and you stop when you sort of feel like it? All right, but that was the state of the art in '95. And so with a few colleagues, Rob Corliss, who's at Western, and Patrizia Gianni at PISA, and Barry Traeger, IBM, we proposed to use some ideas from backward error analysis. And this is something that was seen as kind of dubious at the time, but again, we have to follow the duck. All right, so what we do is we just express the problem in a more well-defined way. So we say, given P and Q, which are polynomials with certain degrees and an error tolerance, do there exist, don't read that, do there exist delta P and delta Q that are such that there's a non-trivial GCD, and if so, find them. All right, so so if we rephrase things in that way, we have a well-defined question, and we can attack this using any kind of mathematical techniques we wish. We're not restricted to saying, you know, pull the ripcord on this algorithm and just it does what it does. And so that was kind of a different way of looking at things. And so then we went on to look at polynomial decomposition, polynomial decomposition together with Mark, wherever Mark is. Oh, there's Mark, and polynomial factorization, and so on and so forth. And so that turned out to be a sort of an interesting start. And in the meantime, there's been a lot of things that come out of that. So, you know, special issues and books and conferences and so on. So that's an example of sort of aiming at something, you know, before the duck got there. I'm going to talk about MathML next. So you don't really need to know what the file name was. Okay, so there we go. So I remember, so one summer when there was some discussion about what should go between the begin and end math tags, I made the departmental T-shirt in the Math Sciences Department at IBM Research with my favorite equations. And so there we go. These are my favorite equations. I was told by one colleague that two of them are the same, which of course is true, but they're still my favorite equations. All right, so what happened was in 1993, actually originating from Gonnet, who'd moved on to Switzerland, there was this open math effort that was initiated for exchange between different parts of let's say, the Maple kernel and the interface. And the thought was perhaps we could get more software elements to participate in this discussion. And that's where the open math effort originated. And that sort of puttered along with a group of, you know, maybe a couple of tens of people worldwide deeply interested in efficient and meaningful data exchange between mathematical software. But shortly thereafter, there was this still this math element left in HTML 3.2 where the meaning of what was to go inside was ripped out. And so there had been a proposal for what should go in the math element, and it was something a little bit like an EQN style language for those who will remember the early days of Unix. So basically it was like a micro syntax to go inside of the math element. And there was this unchartered as yet math working group defining what should be the micro syntax to go in there. And it occurred to me that it was kind of important to get this one right, because whatever happened there was not going to be affecting tens of people. It was going to potentially be involving tens of millions of people. And so I sort of jumped into this group, and the first thing I noticed was this internecine warfare between different groups. The folks coming from the American Math Society who said that anything other than tech had to be vetoed. All right, and then there were the folks from Wolfram Research who had a very nice proposal, which it was just put Mathematica syntax in there, and there was the SGML math working group that had been unsuccessfully flogging the horse of semantic math markup for a decade or so, this ISO whatever subgroup, and it just wasn't going anywhere. And so what I did was I pulled together a group of the players, and I said, whatever has to go in between the pointy brackets to say math and math, that this has to be in the native syntax of HTML. At the time, there's no such thing as XML. And so it has to be in the native syntax of HTML in order that all the tools that we use to do spell checking and traversing the HTML will also be able to descend into the math objects, because otherwise it'll just be an opaque blob and we won't be able to sort of treat it with any of the other document processing tools that are around. Well, it turned out that very shortly thereafter, the XML proposed recommendation came forward. So it was December of '97. One of the authors of that was Tim Bray, one of the first CEOs for MapleSoft and OpenText. He was actually part-time appointed to both of the companies. So he's one of the co-authors of XML. And 2 months after that, MathML came out using this HTML native sense, was now called XML. And MathML is now supported in all the major browsers, computer algebra systems, and it's actually been incorporated. MathML is now part of HTML5. So that's an example of just being lucky, or maybe deciding where you need to go to be at the right place at the right time. And now I'll move on to something which has nothing to do with, well, less to do with mathematics and other things. So there's a company in town here called Descartes, the Descartes Systems Group, and it's not as philosophical as you might imagine. Descartes is a dual-listed public issuer that is a leader in on-demand software as a service, cloud-based, all these things. What it does, it provides solutions for logistics-intensive businesses. Calling it software as a service means that instead of selling you a license to go buy some shrink-wrap software, then we just have a steady revenue stream as a utility. And we need to connect people up to our network of approximately 35,000 trading partners worldwide. These trading partners aren't like you and me. These are trading partners like CVS and Brinks and ocean carriers and airlines. And what these solutions do is to route, schedule, track, measure, and various different delivery resources. By this we mean sort of trucks and so on, to plan and allocate and shipments. So basically we optimize shipments, combine shipments. We'd organize, let's say, future contracts for space in the bottom of a boat that's crossing the ocean, and so on. Okay. File custom. Now, the interesting thing is that we can reuse data for multiple purposes. Like once you know what is inside some transport mode, once you know what's inside of a truck, then you not only have your bill of lading for delivery, you also have information that could be useful for crossing a border if you have to file advanced customs clearance or so on. And so the nice idea is that for every physical object you're moving around, you've also got the information that's associated with it, and that you can reuse this information over and over again, hopefully, to be able to provide more services to the same customers at a better price. And you get stickiness for the customer. And so this is basically an Internet of Things on the move. That's how I think of it. Now, All right, so I've been involved with the company since 2001. I've been chairman, and the company was hitting hard times. The company was initially launched on the promise of the year 2000 was coming and everything was on the way up. And we hit this bubble and everything collapsed. And so I found myself there as a board member as things were, the stock had gone down from highs of in the triple digits to, to $40 at the beginning of 2001, down to like $10 when I joined the board. And then a couple of months later, it was like, $6 and eventually it was down like $1.30 or something. And so a turnaround was needed. Being able to sell promises wasn't enough. To say, yes, we're losing $6 million a month, but we're going to make up for it in volume. That doesn't work. Okay, you have to somehow convince your customers you're going to make some money. And so I was appointed as chairman, appointed Art Mesher as the president of the company shortly thereafter. We went out and we fired customers, the customers that were soaking up all our time and not providing any margin. They were gone, had to reduce staff, had to focus the company, and then start to make a trail of strategic acquisitions. I'll give one example. So something that shocked us all was 9/11. This had a profound impact on the logistics and supply chain world. To begin with, one of the first reactions was to try to lock down the supply chain. And to begin with, there was, in the United States at least, there was a voluntary program where people could go and they could advance file their customs clearance for trucks approaching the border with the promise of crossing the border more quickly. So we went out and bought a couple of companies. Trucks go south and they come north, so we don't have to file customs both ways. So we went out and bought a couple of companies, one each direction. And as anticipated, or as you might have guessed, I think that's the right way, this voluntary filing became a mandatory criterion. And so then we were immediately sold out. We had everybody working full time. And so the idea there is to think ahead as to what is going to be the next thing that you have to do, and you usually don't have enough time to actually go and develop the software or the capacity to deal with that thing yourself. Sometimes you have to go out and some people would even think you're overpaying for something, but provided that sort of is the golden spike that you're going to need in 3 months, maybe you should pay for it now. And that has proven useful time and time again. Since I've joined the board, we've done 22 acquisitions. And so the revenues initially, after firing our customers that were providing top line revenue, but no bottom line, so this decreased our revenues. Revenue's been increasing. And so these are two different income measures. This is earnings before income tax and depreciation and amortizations and so on. This is the actual way the accountants would look at it. But the green line is the important one, and that's going up on a consistent, steady basis. All right, so I'm going to talk about a couple of other very one more mathematical thing here, and that's sort of just one of the things I'm doing now. I gave this talk a couple of years ago called Computer Algebra's Dirty Little Secret. And that is, so here's an expression. This is clipped out of a Maple session. Okay, if I type in, so I was trying to analyze the asymptotic behavior of some algorithm one day, as we all do. And I came with some expression that was not exactly this one, but it was sort of like this one. And I was sort of simplifying it by hand, and I thought, hold on. You build computer algebra systems. You shouldn't be simplifying this by hand. You should put this into a computer algebra system and simplify it. So I put the expression, which was more complicated than this, into Maple, and I tried to simplify it. And I tried to simplify something, you'd think you might use a command like simplify. Or there are several other commands you could use, but nothing ever worked. And the reason is, so computer algebra's dirty little secret is that if you have symbols in the exponents, then the computer algebra systems don't handle them systematically. So if you have, so those of us who remember our high school algebra will remember that the difference of squares can be written as a product. And if n and m are integers, then we ought to be able to always factor x to the 2n minus y to the 2m, like this. And then it turns out that you can sort of develop some theory of so-called integer-valued polynomials, and you can then go off and find algorithms for greatest common divisors and factorizations and functional decomposition, et cetera, et cetera, et cetera. Remember what I said about the approximate polynomials? You can do all the same kinds of things again for these things with symbolic exponents. So this is an example of something which, you know, is still underway. Another thing which I've been working on recently is this area of mathematical handwriting recognition. This is another thing where the jury is still out. So I don't know, you know, a couple of people here have been in a talk where I've shown this slide here, so you're not allowed to say. But does anybody recognize this equation?
E equals MC.
Yeah, E equals MC squared. This is the first time E equals MC squared was ever written down. This is a photo of the manuscript in which Einstein is developing his special theory of relativity. We see that it could have been L equals MC squared. It could have been. But so not only do we need to enter formulas, we also need to be able to do editing and so on. This seems like the perfect interface for a system like Maple. And so I'm not going to give a whole lecture on this, except to say that you end up with interesting problems because you've got hundreds of mathematical symbols, which are all very similar to each other, very many one or two stroke symbols, unlike the Latin alphabet, which has a couple of tens of symbols, or Chinese, where you have thousands of symbols, but there's only 17 different strokes and they have to be written in a certain order. And so it's an interesting problem where you've got a few hundred symbols that have similar number of strokes, many of which look the same. And so the whole theory of natural language handwriting recognition falls apart. It doesn't work too well here. But yet people have spent entire careers in handwriting recognition. So we have to develop some fast, effective ways to get going here without spending whole careers on it. And so an interesting idea was to use some kind of orthogonal function basis that does good separation, and because everything's separable, you've got these continuous deformations between points, and then we can do some statistics. For example, here this is obviously the sum of I over I of I squared, and this is z dot plus z is equal to sine omega t, except for the fact that this z dot and that I are bit for bit exactly the same in the image. So we need to be able to sort of, not only do good character recognition, but have statistical methods for combining these things and so on. And some people don't believe that handwriting will be the way to interact with our math systems in the future, and some people do. The jury's still out on this. All right, so that's been a few stories. I'll just say, because we're at a university, there's some things about teaching, some thoughts on teaching. One of the first things I did when I came to Western was to launch this joint program in computer science and law, because at IBM Research I'd seen wonderful, featureful, interesting things developed in the labs, and figuratively they'd get wheeled out to the loading dock and the lawyers would come at them with chainsaws. And at the end you'd end up with this little stump of something that used to be good, and then IBM would try and sell it. And guess what? It wouldn't sell. And then people say, see, you researchers, you just can't do anything for us. But the real problem is that you've got a contract that's some formal structure with some grain to it, and you've got some technology, some piece of software with some formal structure to it. And if you put the two together so that they're cross-grained, and you need to take something out of this piece because of, then you can't move. And so the thought is that as we move forward and as technology touches every aspect of our lives, then we're going to need people who understand not only that software is a thing, but also understand software in a deeper way, and also have legal background. Another program that we've also at Western, we had the first year students entering the Faculty of Science in 2011-12. We had 400 students entering to study a Bachelor of Science degree, and we had 1,000 students who signed up to take what's called a Bachelor of Medical Science degree. So basically, to first order, every first year science student at Western thinks they're going to be a doctor. All right? So what do? You create an entry-level course in medical computing. And people said, what's that going to be? And I said, I don't know. It's just got to be called medical computing. Okay, and so then I threw in some crypto for medical record security and some radon transforms for figuring out how to do CAT scans, and we did a bunch of robot guided surgery and various different things like that. And in the end, we've got a course that the students seem to like. So scorecard here. Some things seem to have worked out. The timing seemed to have been fortuitous with Maple, symbolic numeric algorithms, MathML, the stuff with Descartes. Some things were clearly too early or just not aimed right. I don't know anything that was too late, like we started too late. But some things the jury's still out because we're still working on them. So let's come back to our duck shooting. All right. So the wisdom that we learn here is that no one can tell you how far you have to aim ahead of your target. Okay, you just have to figure that out by trial and error. And that when you miss, the odds are that you didn't aim far enough ahead. Okay, it's not that you didn't aim far enough behind, you didn't aim far enough ahead. So remember how the ones you hit looked to you over the sights, and do it again the same way. This is our friend Henry Davis's comments. Now, another aspect is about the trigger pull. This is also true when you're involved in a research program or developing software, and that is it takes you longer to get the trigger pulled than it does for the load to travel. So once, there's a lead time in getting your stuff ready. And you have to take that into account before you shoot. And he goes on to say that no charts, diagrams, tables of figures will give you the remotest idea of how to hit a flying object, which is flying differently on every shot. And I think that's true as well. So you have to be able to figure out when things are different, when they're the same. And that's all I'd like to say today. Thank you. Are there any questions? Any duck shooters, quail shooters in the Ian?
Do you think that a lot of the efforts in symbolic computation, I'm sitting in an awkward place to ask this question, from the early 70s were too far ahead of their time for the resources?
Well, that's clearly true.
And could it, if your goal was, what would you do in that situation if we transported you back 40 years? Which, by the way, we're going to after the talk.
Oh, fabulous! All right, let me just sort of take some ticker notes here. Perhaps the most telling example of this is that there were a couple of Fortran-based systems. There was the SAC library, developed by George Collins and his students, and there was Altran, developed by Brown and Feldman at AT&T. And these were essentially Fortran-based environments that were using whatever technology substrate was available at the time. And they were able to handle polynomial systems reasonably well using good algorithms. The format style things that were doing general expression manipulation didn't have the algorithms to work with these expressions in an effective way. So you hit expression swell immediately, you could barely do anything. So I remember some people doing relativity calculations using Formac and so on in the 70s, and they couldn't really do very much. But the polynomial stuff was pretty well understood, but I think as with many things, the development cycle was so long because, even in terms of what you would now sort of say, hit enter, look at it, okay, try it again, hit enter. And so that was like in the order of weeks instead of in the order of seconds. The interesting things with working with more general families of expressions didn't really get going until the late 70s, I think. That's when it became possible, and it clearly came along with the technology. And I think that we're also missing the boat today. That there are things that you could look back and say, oh yes, well, we can do all these things now in the year 2012 that we couldn't do in the year 1980. And that's, we pity those people in 1980 because they weren't able to do those things. Well, people are going to look back on, we ask ourselves, what are people going to look back on now and say in the year 2012 that those poor people should have been doing but weren't? So, for example, the Sloan Foundation has just been requesting suggestions on how to create a world digital math library with all of the research mathematics that's ever been published to be available. Now, if we look at our math systems now, our computer algebra systems, then we're still stuck in sort of the 1980s dialogue where we type in an expression and we simplify it, then we look at it and we decide whether we want to factor and so on. And the interesting and exciting math that people are largely engaged in today involve collaboration between people. And so if you're sitting in Waterloo and I'm in my office in London, we should be able to work on a proof object together. And so maybe you do some exploration on some aspect of it here, and I do some exploration on it here, and then we add to it. And if Facebook is able to keep a dialogue going more or less reliably between millions of people, we ought to be able to have a mathematical dialogue between tens of people well supported. And to be able to, instead of just, like even in a system, in a computer algebra system today, when you say you've got some Bessel functions in here and you want to be able to do some simplification, then well, you can look up the Bessel commands in the help library. You can look in the online dictionary about Bessel functions. Go to another place. And so the idea that saying, well, I've got this here, can you help me figure out how to deal with it and to connect to the literature and in a more unified way. We've got a forming semantic web out there. And if, mathematics ought to be one of the seed kernels about which this semantic web accretes. And so I think that when we look back in 20 years and look at our computer, or 40 years, look back at computer algebra systems today, we'll see them as being as impoverished as we look back at the Fortran library. So yeah, I think it's partly due to resources, but also partly due to ill definition of the scope. So the scope was too coarse back in the early 70s. People tried to either do just polynomials or everything. And the idea of carving out something that was well-defined and a little bit bigger wasn't tried so often. The folks at Cambridge with Camel did that nicely by working with Fourier series and so on. Kesha.
So, continuing with your duck shooting metaphor, I have two sort of related questions. The first one is, when do you know the duck is dead? So there's no point in shooting anymore. And second, when the duck is dead, you choose geese or skeet. What area do you choose next?
Oh, okay. Oh, that's a very interesting question. How do you know when the duck is dead? Well, I suppose there's some facile answers, such as if you don't hit it, it's not dead. But that does beg the question that you might actually have a duck that's not actually alive traversing your line of fire. And so I think that it's important to consider that also. There's some problems that you should not even try to shoot at because even if you solve them, so what? There's nothing in it.
Or it's been so thoroughly solved that you're just adding an epsilon to the...
Right. So I would think of that as hitting the tail feathers as opposed to having a dead duck actually flying. But yeah, so how do you know when a duck is dead? That's a deep question. I suppose I've been presuming that we're able to identify a duck that is living when you first see it. And that's a different problem of understanding when it's a dead duck that's going past. It's an important problem. I remember at IBM Research, Bill Polyblank, as a young guy, he said, you can't just work on every problem that crosses your desk. You have to decide, where your time is best spent. And that's an important advice for us to give to our junior colleagues, either in research or in business or anywhere, that we've only got a certain number of heartbeats and we have to decide where to spend them. So that was the how do you decide when the duck is dead? Well, that's a different question. I think you have to decide. Now, let's be grotesque to sort of go into this analogy too deeply, but you have to look at it and think about it. Is this really got a lot of life left in it? Yes, it's still flapping a little bit, but And the other question was about geese. Well,
if the duck is dead, you decide it's dead, then you choose
Right.
to shoot something.
or another duck, or a different geese. Yeah.
Yeah.
So yeah, I think it's absolutely key. Now, going out and finding the ducks is a big part of the name of the game, right? Deciding that this is an interesting thing to work on is a different thing than once you've decided to work on it, to decide where to aim so that when you deploy, you'll hit that sweet spot. It's an important question. I don't have a magic answer for it.
Maybe you can ask it to follow up with that. Because you went to Descartes, right? I mean, it was an obvious career choice to see you go from solving symbolic math running a company.
Oh no, I didn't actually go to Descartes as a career choice. What happened was back in 1998, there was a crisis at MapleSoft, and the half of the I think all of the board of directors resigned, and so did the president of the company, and the company, and so there was like an emergency board pulled together, and I was one of the people that was called in, together with a fellow by the name of Peter Schwartz, who was the then president, CEO, and chairman of Descartes. And that combined role is frowned upon in today's governance world, but that's the way it was then. And so there we were in the MapleSoft boardroom, and people would be making these proposals and so on. And because I didn't live or die by my participation in boards, I was able to therefore say what I thought. And so when people would say something that didn't make sense, I would say things such as, "That doesn't make sense. Could you explain it to me, please?" And they'd say, "That still doesn't make sense. Could you explain?" And the colleagues would be there, come on, don't push this point. And they'd say, "No, really, I'd like to know." And then they'd say, "Oh, well, maybe it doesn't make sense after all." Okay? And so when there was a board vacancy on Descartes, then Peter asked whether I'd join his board. And I'm not so naive as to think it was because I was, insightful, brilliant person. They wanted to have like a team academic they could sort of keep under control, right? And so it's the same thing. That doesn't make sense. Hang on a second. What were you going to? And so then 2 years later I was chairman of the board. But it was a moving time, and I don't think it was not because I was the brilliant strategist. It was because everybody else had a bigger liability target pinned to their back. And so, when it came time for someone to step up, everybody else scattered, all right? And so maybe being a bit picturesque, but that's, I think, to a first approximation how it works. And so the career choice to go to Descartes was really just, it seemed interesting. It's a math, there's a lot of math there behind the scenes to do route optimization. And then it becomes an interesting business problem of how do you reuse this data in ways that will sort of escalate your ability to serve the customers. So it wasn't really a decision to drop everything and go to Descartes.
Any more questions? What are tomorrow's flying objects?
Oh, okay. Well, if we knew tomorrow's flying objects, we would all be away working on them. I can think of some things that are going to be too far out. There was an interesting comparison of what Facebook is doing versus what Google's doing with the idea of computer vision. Right? So we've got so Facebook is now the largest photo site. You might think that Flickr and Picasa and so on are big photo sites, but Facebook is actually the largest photo site. And so what's going on there is to try and do to match, identify people in photos and so on and so forth. And so that's really sort of a syntactic analysis of the images. And as we've seen with the Google glasses and all this, that we're looking at actually sort of image understanding, to be able to sort of see what's going on in real time with what people are seeing, to be able to, we've got, imagine if you're wearing your vision capture device, then you've actually got your life data stream as opposed to a few photos you've picked out of your telephone. So that's the scale of kind of questions that we're facing now. It's always a temptation to sort of not think far enough ahead, or to think way too far ahead. And it's a very high condition number on that, where we go from like too easy to impossible in one step. And so it's very, I can't say in real time, like, slice that thin enough to hit the right spot. But we need to clearly take into account the increasing connectivity with all of the objects in our life. And imagine if you're able to, instead of, I'll look at, let's say, the shipping space for a moment, not because I live there, but just because we talked about it a moment ago. We've gone from having a paper manifest to slapping an RFID chip onto a pallet. And now, suppose instead of putting a $1 RFID chip on a pallet, we're able to put a $10 Raspberry Pi kind of thing on there. And so now instead of saying, oh, yes, we can figure out exactly which truck the spoiled produce is in, we're able to have the pallet of goods say, help, help, I'm melting. Okay, because it's got a $10 computer on it, which is able to communicate to us, rather than an RFID chip that says, "Yep, I'm the one who's spoiled." So that's I think just one example of the how we will see our world change. What is where did the plastic in this bottle come from? Can it go into a landfill? Can it be used to hold potable water again? So imagine using crypto systems for chain of custody management. And so every object has some signature on it, and you can tell whether or not this really is one of the 5 whales that was slaughtered legally or something that was poached. And so I think chain of custody is an example where computing will figure in surprising ways. Just a couple of little examples. I don't have a magic crystal ball.